Hey guys, quick note. I was having technical difficulties with this lecture recording, so I'm doing it again. Um, in class, I had a few uh, physical demos, some things that I passed around, and we also had a quiz this day. So this is going to be a fairly short recording, as I'm going to redo this right now. All right, but we're talking about thermal physics. So we've looked at fluids, and solids and states of matter, and I told you that adding energy to something might change its state. Maybe it's a solid, maybe its atoms are very structured, its molecules are in a very structured way. You add some energy, you sort of excite that structure. All of those molecules, they all start to move around a bit, become more excited, and then they become a liquid. They're free to move around. This sort of movement of all of these particles or molecules, that is due to this energy that's absorbed into the system. So let's look at a little bit more on temperature in something called the zeroth law of thermodynamics. I just have zeroth law up at the top. So us as humans, so this is going to be very general, we can sense temperature very, um, I say, very roughly. We do a good enough job at sensing temperature. So, you might go outside and maybe you right now, you can tell what the temperature is going to be today. Maybe you looked it up before. But do you know exactly when that happens outside without looking at your phone or something? Or for the room you're in right now, do you know exactly what temperature the room is right now? Or maybe, put your hand on the desk. Do you know the temperature of that? Does it feel different? So us as humans, our senses, we can roughly tell hotness and coldness, and it's good enough for us to survive. I can tell that I can't hold, something that's burning for too long before I start to feel, severe pain and I have to, drop it. Same thing for things that are very cold. Um, I also told a little story about people who have experienced like frostbite conditions. They've reported that it feels like a burning sensation, and that feeling we get that's related to burning. That's just the skin cells dying. That's not a you know uh, really accurate reading. So we could get that mixed up if it's hot or cold. So us as a human, our senses are good enough. We're not good at telling actual values or exact values. We can't really label it with a number without being more scientific about it. So how do we actually do that? How do we actually make something that can accurately tell temperatures? I can, maybe the room you're in, you could say it's one temperature and you go to another room. How do you actually do these temperature experiments when our senses are so, vague and so general? We need to create some really, strict rules for us to follow because our senses are not good enough for us to make measurements off of. So we need to define something called thermal contact. So if two objects are in thermal contact, that means that they are able to transfer energy between them. So I have this blue and yellow sort of cubes here, and it doesn't matter which one's hot or cold. Just note that they're different, and there's this thermal contact between the two. They're able to transfer energy. They're able to exchange energy between them. If there is no transfer of energy, but they are in thermal contact, then that means these two objects are in thermal equilibrium. So that's kind of like this picture right here, where these two objects, they could transfer energy, but they don't, because they have the same amount of energy for both of them. And if we look at how this applies to like the real world, objects almost always want to try to be the same temperature as another. So I have an example here of a hot cup of coffee or tea. It sort of lets off steam into the room. You might walk away from that coffee for a little while, and you'll know when you get back it's going to be cold again. So the coffee is trying to be the same temperature as the room. And the room is also trying to be the same temperature as the coffee. But the thing is, there's a lot more volume of air in the room than there is volume of water in the cup. So typically, you have this hot thing, you leave it in a room, it will become the temperature of the room. And if you had a thermometer with you right now, you could actually go around your room right now and pick any object, your table, any part of like the door, the floor, all of the objects in your room are the same temperature as each other because they've been given time to reach this thermal equilibrium with one another. There's no more transfer of energy. So all objects are trying to reach this equilibrium point. If you were to sit in your room for long enough, you would eventually become the same temperature as your room. But our bodies, produce our own heat, and we don't quite get there. So we have that. Next up, we're going to see how can we actually measure this. I'm saying energy is flowing between one thing and another. I see thermal equilibrium. Objects want to be the same. How do we actually assign values? How do we take measurements? How do we even do science around this? This is just a vague idea right now. So let's take this idea. We're going to keep working on it. I'm going to say, what if we take two objects and I'm going to call them A and B. It doesn't matter their temperatures or anything, any actual values right now. I'm going to say they're different temperatures. And they're not in thermal contact with another. So let me actually write that down. So the two objects A and B, A and B are not in thermal contact with each other. Or I should say each other. Okay. So they're different temperatures and they're separated. So they can't exchange energy right now. You think this is sort of like a perfect system, they're not going to lose any energy, they just stay their own perfect selves separated. Okay. How do we maybe we can make a tool to help us figure this out. So what we're going to do is we're going to introduce a new object. We're going to call this object object C, and typically this object will be much, much smaller than the objects A and B. And it has its own sort of internal energy. I just colored it gray, and you could disregard that temperature. Whatever object C is, it's not important right now. What we're going to do with this object is we're going to use it to sort of make this calibration, and I'll explain this next step. So we're going to take object C, and we are going to put it in thermal contact with A. And we're going to wait until C and A are in thermal equilibrium. And so they were together and they sort of exchanged energy. The energy flowed throughout the two, and then they reached a thermal equilibrium. So now they're the same. And what the important thing I'm going to do here is I'm going to mark down this value as a reference point. And that's basically for me to say that when C is equal to A, it looks like this. And I just have it as the color blue. So when C is equal to A, it looks like that color. Or maybe if I have this value and I assign it a number, I say it looks like this number. Okay, that's interesting. I'm giving it a value, a number. All right. Now, what do? We take object C and we do the same thing, but then we take it over to object B. We put it in thermal contact with object B, and we wait for them to become in this thermal equilibrium. Thermal equilibrium, that means they're not exchanging energy anymore. So at this point, object C has become, it's in equilibrium with B. It's pretty much the same as B. And I'm going to mark this value down as another reference point. And what I'm doing is I'm saying, well, when object C, when it looks like this, for that first test, when it looks like that, it will be, kind of this blue shade. It will look like object A. But then when it's this other shade, when it's yellow, or maybe when it's this number, it is the same as object B. What I'm doing is I'm doing these two calibration points. Let me show you with this next slide right here. So by adding those reference values, those values that I marked down, I just give them a number. I could give them any number I want. I could say object A is 0 degrees. That's just a value that I gave it, just because. You at home, you can make your own number scale if you wanted to. I say when object C looks like this, and I say it's that number, whatever that number is that I gave it. When object C looks like this, oh, that just means it's 0 degrees, or it's this temperature. And then when I use object C and I say, oh, it looks really yellow, it looks like this, it has this number, maybe it's a number up here on this number scale. When this object C looks like that, I'll be able to tell the difference, and I could say that I've just made a thermometer. So I've turned object C into a thermometer. So this is basically how thermometers are made. We have, some reference point. We say we put this you think of a classic thermometer with maybe mercury or alcohol in it. The level has to get down to this certain point over here, and right at that point, we're going to call that 0 degrees. And then right as maybe we have this thing that's constantly boiling over here on the right, and when it gets over, when we have this thermometer in there, we see that it's boiling, then we're going to mark that as that specific value. And that's how thermometers were made. They're calibrated that way. We'll get more onto the actual scale in a minute. Let's talk about that 0th law that I brought up in the beginning. So we have, let's say we have this thermometer. Let's say, it's object C. That's our thermometer, sure. And we want to measure 2 different materials. And let's say we take object C. We take object C and we bring it over here and we do that same test that we did earlier. We have C, we get in thermal contact with that one. Thermal contact with that one. And we wait for them to become in thermal equilibrium. You imagine they'll both turn a shade of green. And then we do the same test, with C and B over here. Same thing with thermal contact. We wait for them to become in a thermal equilibrium. It also become a shade of green. Well, what I'm doing here is I'll see that if I have it spelled out here. If C is in thermal equilibrium with A, so let me put it up here. If C equals A, and if C is in thermal equilibrium with B, and if C equals B, then objects A and B are in thermal equilibrium with each other, even though they're not actually touching. They're not in thermal contact with another. So this is like a classic math thing. If C equals A and if C equals B, then that means that A equals B. And that's the 0th law. I think I didn't read too much up on this. I think it's because why it's called the 0th law. So they've already started at the 1st and 2nd and 3rd law. They already established those. And then they've figured, well, this is something that's also true, and we don't want to call it the 4th law. And this law, it seems a bit more basic, a bit more fundamental. So let's just make it actually before the 1st law. Let's make it, the 0th law. I may be completely wrong on that. I'll have to look it up. So we have this, we've looked at thermometers and the 0th law. Let's look at temperature scales. So we created a thermometer, but why do we use the units that we do? So the Fahrenheit temperature scale is created by Daniel Gabriel Fahrenheit. It is based off of the temperature of a saltwater and alcohol solution. So pretty much it had a big batch of this solution, a big mixture, and he was doing that test when the solution just started to freeze. It just started to turn icy. He said that's 0 degrees, and he said I need to give this a unit. Well, I'll just use my last name. Sure, Fahrenheit. 0 degrees Fahrenheit. and I don't quite know the reason why. Maybe he's into biology. He wanted to calibrate it to a human body. So human body temperature, he took someone's temperature and said that temperature right there, for this thermometer that I'm making, that temperature, where the mercury lines up, I'm going to mark that line as 96 degrees Fahrenheit. Exactly. And that's actually a little wild to think about. He just picked some person to create the scale of this, thermometer he's making. So, as we know now, I don't think we knew quite as well then. Every human body has a, slightly different temperature that it's accustomed to. So every human body has a different, resting body temperature. It's all around 97, 98, sure, but it's slightly different. So having this temperature scale and just picking some random person and calling this 96 is a little crazy. Something that makes a little bit more sense is using the Celsius temperature scale. This is based off of the phase change of water, and water is the most abundant sort of thing on Earth. I just call it the most abundant thing on Earth. Its freezing point, everyone will know, is going to be 0 degrees. So we'll just call that 0. Changes into ice. That's easy to see. That's easy to measure. I'm going to make it easy to measure because I'm going to call it 0 degrees Celsius. And then when water, the most abundant thing on Earth, starts to turn into steam, I'm adding so much energy to it, I'm going to call that 100 because that's easy to deal with. 100 degrees Celsius. So by far, Celsius is much easier to deal with. It's like the metric system. It's only, it's based off of 100. Very easy to read and to work with. Okay. If we want to go from Fahrenheit to Celsius or Celsius to Fahrenheit, we can use this conversion rate right here. So I'm going to put, so the temperature that we have in Fahrenheit is equal to 9/5 times the temperature we have in Celsius plus 32. All right, it's a bit complicated, just going from one to another. Yeah, so by the way, just add an extra thing. For this Fahrenheit scale, the freezing point of this salt water solution, let me do this in red. So the freezing point, this really weird salt water alcohol solution, he said was 0. The boiling point is around 212 degrees Fahrenheit. Just a little extra tidbit. So we have this temperature scale, Fahrenheit and Celsius. There's also one more scale I want to introduce. So using a more advanced method, we're using, think about using something like pressure, and maybe we could measure the volume of something. When the volume increases, I'll say that that's this temperature. And when the volume decreases, I'll say it's that temperature. So imagine using a volume-based thermometer or a pressure-based thermometer. Using these more advanced methods, we found there's actually a limit on how cold we can get, on how cold something can get in the universe. So there is an actual limit on how cold something can get. The coldest possible temperature is minus 273.15 degrees Celsius. So it won't go negative forever. It has a limit, minus 273. And this is what we've called as absolute zero. That is the coldest possible. And since this is the coldest thing, physically possible in the universe, we said, hey, well, we want to keep things easy, right? Well, let's say that the coldest thing possible, nothing can go below it. Let's call that absolute zero, and let's make that a new temperature scale. So I'm going to say that when something is 0 Kelvin, so something that is 0 Kelvin, that is absolute zero. And each degree, we already like that Celsius thing that we made a while ago. Let's keep the same size of the little markings. Let's keep them the same spaced apart. So what that means is it's a very easy conversion to go from Kelvin to Celsius, or the other way. So we have the temperature in Kelvin is equal to whatever temperature we had in Celsius plus 273.15. So you can imagine if we had 0 degrees Celsius, the freezing point of water, well, that's just going to be 273.15 degrees Kelvin. Typically, we just say Kelvin. I don't think we say degrees Kelvin. Right, so it's a very easy conversion rate down here. And you'd use Kelvin. We're going to be using Kelvin a lot in this in the next chapter. And you'd use Kelvin in like anything with dealing with astronomy or any very large or very, very small temperatures. Most on-Earth sciences will probably resort to using Celsius. However, it is common to use Kelvin. In almost any science, it's almost never helpful to use Fahrenheit. Okay, so we have temperature scales. Let's look at one more thing. This is going to be the last thing. As imagine the mercury in that thermometer that I just had like a little picture of. What's actually happening there? Mercury is a metal. It's a metal that is liquid at room temperature. That's really interesting. And if you maybe take some of that mercury and you trap it, you put it in this little glass container and you warm it up, what's happening is this liquid, this material, is going to expand. And that's why when something maybe like a gas in a balloon, or maybe you have something that you heat up, like imagine a steam in a was it a railroad car. If you heat something up, it expands and builds pressure. This is the same thing that happens with solids. So actual solids will expand when they warm up. Like at the very beginning of this sort of talk, I said Solids have this nice rigid structure. They do allow for some expansion. So they might grow and shrink, maybe just a little bit, but every small little shift can add up and add up and add up over the millions of molecules, millions and billions of atoms that make up, a solid material. So if each one of them shifts just a little bit, if each atom expands and shifts just a little bit, it can really add up. And some proof of that is right here. So I used to go to Fresno City College as an undergrad, and there's a railroad track that goes by. And if you've ever heard a train go by, you might hear this sort of clicking and clacking noise as the train sort of whizzes past. What that is the railroad tracks themselves have to have a certain spacing between each metal beam. So there's a big metal beam and there's like a tiny little spacing that you could probably fit like maybe a quarter or two through. And that creates this clicking clack sound as the train rolls over top of it. But if you place the railroad lines, if the iron beams, steel beams, too close to one another, and you don't give them that space, when the sun beats down on it, when the day gets hotter, the metal in the railroad line will expand, and they're going to press onto each other, creating a lot of pressure and actually starting to become very destructive. You can see in this little video right here of what's happening. And then so the train rolls on top of it, and the metal in the beams are trying to expand, but they can't. So they have nowhere else to go. They're going to bend. We get this actual bending of railroad track lines. So it's very, very destructive. It goes on over here. Same thing happens with like concrete and pavement and everything. That's kind of why we have these lines on sidewalk paths. So we could have this room for expansion between things that are going to expand, and if things get really cold, things will contract a little bit. They'll sort of shrink. On bridges, you may see these sort of grates that go across them that allows for expansion. When the metal in this bridge starts to expand just a little bit, it needs room for it to expand into. Yeah, so I thought that was really interesting. And I think, let me see, I think that's about it for today. So it's at this point where I handed out a quiz. Yeah. So hope this was an enlightening redo of this lecture. I think this one was a bit better than the in-person. I was having a lot of technical difficulties. But hope you guys have a great rest of your day. I'll see you later.